Okay, we're starting chapter 1 today, talking about derivatives. So how do we understand the word derivatives? It's a rate of change, right? So derivative means the rate of change. The rate of change. Okay. Actually, we already know. I will see. So it's the rate of change of something, right? If you drive a car, the speed of your driving. So we're going to cover all the sections, section 1 through section 8. So the first derivative is the slope of a straight line. So remember we have y equals mx plus b form. The m slope is the rate of change, is the derivative of function. So when we talk about derivative, so we talk about the derivative of a function. Right? Remember the previous classes we were talking about functions. So everything from now on is built upon functions. So derivative, the derivative of functions. So the first function we encounter is straight line. There's a picture. It's a linear function. So the first one is straight line. It's called a linear function. So given an example, f of x equals to 2x minus 1. So when we graph it, that's a straight line. We graph it as a straight line. So in this case, we see the slope is 2. The slope is 2, right? So we use the red as slope m equal to 2. So this, what does the slope measure? The slope measures the rate of change of x with f of x. So how fast when x change and does f of x change? So rate of change. So if we ignore this, right? If we ignore this, so we divide by 2, divided by x on both sides, we see f of x divided by x equals to 2. So it's a ratio, it's a rate of change, right? Then, so section 2, we talk about the slope of a curve, at a point, right? Let's see if we have some function like this. Right? Maybe we want to talk about what's the rate of change? Like if we imagine a person walk on this path, what's the speed of this person is walking, right? At this point, at any point. We see if it's a straight line, if a person is walking from here to here, the speed is the same, right? Because the slope is 2, it will never change. The speed is the same. Okay, we'll talk more about that. Now let's go to each sections. So all those are straight lines, right? The blue color line is a positive slope, which means a positive relationship between x and y. When x increases, y increases. The purple color is a decreasing, which means x and y has opposite relationship. When x increases, y decreases. Okay. This one, L1, L2, both increases, but with different kinds of speed, right, with different slopes. So this is how do we measure slope, right? Slope is rise over run. From one point to another point, how much do we have to rise up? How much do we have to run? Run to the right. Well, we see the points on this. So this is a curve, right? This piece of string is not a straight line, it's a curve. So we can talk about the slope of the tangent line. Well, speed or the derivative at the point, or the speed of a person walking at this point. So when it's a curve, we talk about the rate of change at this point, or the derivative at this point of a function of this function, is the slope of this tangent line. Tangent line, which means this line touches the graph at one point. Right? You see this line touches this curve at one point. So this line is called a tangent line. Right here, tangent line. The tangent line, so any line has the y equals to mx plus b form, right? Any straight line we can write as y equals mx plus b, or f of x, a linear function. And then what is the derivative at this point? What is the rate of change at this point? That's a slope, m. And we will talk about how to get this, how to take derivative of a function at a certain point. But this picture shows us the changing, right? You see, imagine a person walking from here, a person walking from here to here, right? At this point, what is his speed at this point? Same thing. You imagine walking from here to here, right? At this point, what is his speed? Same thing here. At this point, what's the speed, right? So the tangent line to the curve. So this is a definition. The slope of a curve at a point P is defined to the slope of the tangent line. Right? So the slope of the curve, only this book talks like that. No other math books talk like that. So we see the derivative at a point of a curve. We use the word derivative. Maybe because this book hasn't defined yet, so it's trying to use slope. Slope usually is only for tangent line, for straight line. Straight line involves slope. A curve does not involve slope. But I don't know who, who. Okay, anyway. So let's see this one, this example. So given this function, quadratic function, x squared, right? We're given a point, 1, 1, right here. And we want to find the slope of the tangent line, right? The slope of the tangent line. So the slope of any line equals to changing in y. Remember the difference given 2 points, right? Any 2 points at the line, we find the difference in y value divided by difference in x value. In this case, we see this one is 2. So this is rise over run. Let's see. So we take this point on the straight line. So these 2 points. Right, this point is 1, 1. This point is 2, 3. So you see this point, the coordinates is 1, 1. X value is 1. Y value is 1. And this point, X value is 2. Y value is 3. Okay, so we have 2 points, 1, 1, and 2, 3. So the slope equals to, or maybe we'll call the first point, call this the second point. So we have y2 minus y1, 3 minus 1, divided by 2 minus 1. 3 minus 1 is 2, 2 minus 1 is 1, 2 divided by 1 is 2. So the slope is 2. Okay, when we talk about slope, right? Again, we call the rate of change. So slope as a rate of change. Or later on, we're going to define rate of change as a derivative. The rate of change on this point is the slope of the tangent line, okay? So let's see this question. What's the slope of the graph at this point? So given this point, then we want to find the slope at this point. So what do we do? So this one is in the coordinate of this, the x value is 3/4, right? So the slope of y equals x squared at this point is 2 times this. I don't know how they come up with this solution, but which is the right solution? Which is the right solution? So we'll skip this. I don't know how this textbook comes up with these two, which is right, but it's premature to mention these two here. So far we know the rate of change for linear function is a slope. The rate of change of a point at any function curve, at any curve, is the slope of the tangent line passing the point. Now let's talk about the limits and the derivative. So last class we have mentioned something called quotient, differential quotient. So this textbook acts differently. Okay, anyway. So this again, remember we have this linear function, right? A straight line. And what is the rate of change? So the rate of change from this moment on, we can call derivative. The rate of change of a function, rate of change of linear function, the derivative of the linear function is the slope. Okay, so we write like this, f prime of x equals to m. So we need to get to two notations. Whenever we talk about a derivative, okay, two sets of notations. One, we use f prime of x to mean the derivative of a function f, or the rate of change of the function f. Or another one, we do df dx. Df dx of x, or sometimes written as d dx f of x. Just a notation. So all these three means derivative of a function. Just notation. So in linear function, the derivative f prime of x just equals m. Or maybe we can write it as df dx of x. Or we can write it as d dx f of x. So three notations are equivalent. So slope of this constant function is 0, right? Because what's the coefficient of x? X disappears. You know who disappeared x? 0. 0 times anything would be 0. So the constant function has no rate of change because it doesn't change. It's constant, right? It's a forever b. Right? It's always b. It doesn't change. So constant function, the rate of change is 0. It does not change. That's why it's called a constant. So we can write f prime of x equals 0, or d f dx equals 0, or d dx f of x equals 0. So that's a linear function, right? Quadratic function. The derivative is 2x. Later on, we're going to see y is 2x. We're going to do some calculations. But to write this, we just write a d f prime of x equals 2x, or d dx f of x equals 2x, or df dx of x equals to 2x. You see, it's a function. It's still a function, right? It's still a function. So if it's constant, let's say equals some c, derivative is 0. If the linear function, let's say you have 2x minus 1, derivative is constant, it's 2. If it's a quadratic function, in this case, x squared, right, derivative is linear. So that gives us a pattern. So derivative is always 1 degree lower in polynomial family. In polynomial family, so the derivative function is always 1 degree lower than the original function. So of course, once we have the variable x, so the derivative really depends. Right? The derivative depends on the x value. Imagine we have a quadratic function like this, right? Each x value, different x value will give us a different derivative, will give us different rate of change. Keep going with the polynomial. So derivative of polynomial degree 3 is a 3x squared. So that has f prime of x equals 3x squared. All right, now we can learn the derivative. The first rule of derivative is called the power rule. So if we have a function like this, f of x equals x raised by r, then its derivative is r times x raised by r minus 1. Let's see f of x equals 2x minus 1, right? So according to this function, let's forget about this negative 1 for now. So the derivative equals to 2 multiply, well, this is x raised by 1, right? 2 times 1 times x raised by 1 minus 1. See this r minus 1. Then 2 times x raised by 0. Well, x raised by 0 is just 0. So 2 times x raised by 0 is 1. So 2 times 1 is 2. So now we know where does the 2 come from, right? Before, remember? So, but mentioned a little earlier is kind of premature. Well, let's see f of x equals x squared. Right, so derivative equals to, well, this is 2. Right, we'll move 2 up front. You see this r. We'll move r up front. Then x raised by 2 minus 1. Well, 2 minus 1 is 1. So that's just 2x. If f of x equals x cubed, we follow the rule. F prime equals move 3 to be coefficient. Then x raised by 3 minus 1, which is a square. So 3x squared, so on and so forth. Then let's see this question. If f of x equals square root of x, what is the derivative then? Well, first, this function can be written as x raised by half. So we're going to follow the power rule. So move half up front, then we minus 1 from half. So get a half x raised by negative half, right? Because half minus 1 is negative half. Then what does negative number do? Negative number is seen 1 divided by x raised by a positive half. Well, what's positive half? What's x raised by half? Square root of x, right? So the derivative is 1 over 2 times square root of x. So we just follow the power rule. Let's see this one. Right. If a function is x 1 over x, so we can write it as x raised by -1, then the derivative are going to follow the same power rule. We move -1 up front, then we -1 from the exponent, so we get a minus x raised by -2. Okay, so that's -1 over x squared. Of course, x cannot be 0, right? That's the domain of this function. So derivative of a function is the slope of its tangent line. Let's see this question. So we need to remember this. Okay. The derivative of a function at x equals to slope of the tangent line at x. So what does this mean? Let's see, I have a graph like this, right? I want to find the derivative at this point, at a certain point, right? So how do I do that? That is, so we're going to see two ways. We have two ways we're going to use the power rule for now. Is the slope equals to the slope of its tangent line touching at x, at this x. So this, the x value. Okay, now find the slope of the curve. Y equals to 1 over x at 2 and a half. Remember previously, we already know the derivative of 1 over x is 1 over x squared, right? We can write as y prime. So this is y, we can write as y prime. And then we just plug in the x value. X value is 2. So we get -1 over 2 squared, which is -1/4. And that's it. But usually we don't call the slope of the curve. We just see the derivative of this curve at x equal to or at this point. So that's the graph showing, right? At x value equals to 2, right? What is the rate of change of this point? Right? Imagine a person walk from left to right. How fast is this person walking at this point? Let's see this example. And we want to find the equation of the tangent line at a given point. So we're still having given this function 1 over x, rational function. We're given this point. So we want to be able to write y equals to mx plus b for the tangent line, right? If it's a straight line, it always had this form. We need to find m, we need to find b. So m, where do we draw m? M is the derivative of this function, right? We already calculated. We see f prime of x equals to -1 over x squared from previous example. Now we evaluate it at 2 because the x value equals 2. That means we plug in x as a 2, which is a -1/4. So that means the slope is just -1/4. So we can write as y equals to -1/4 x plus b. Then how do we find the b? Because we know this point. We're going to use this point. Right? So y value is a half. X value should be 2. So then b equals to half. Well, -1/4 times 2, -1/2. So negative, we move to the other side, become positive. b equals 1. So what's this? So the tangent line we're looking for is negative quarter x plus 1, right? Because we find the slope through taking derivatives. We find b through plugging this point. So this one is a similar. I'm not going to do this one. But for you, you should go through the example. So this is the equation of the tangent line. So we could do this, right? If we know the points a and f of a, it is y minus f of a equals to, so where does this come from? Remember f prime of x equals to the slope. The slope is difference in y value divided by difference in x value, right? Here, do you see 2 points? We have x, y as 1 point. We have a, f of a as another point. Okay. So that means this one, so y2, so this, let's call this a second point. So y minus f of a divided by x minus a. Then we multiply x minus a on both sides to get this. Okay. Because this f prime of a is a slope m, so it's still using the formula. Let's use that for this example. Okay. We have a, we have f of a, or another point just x and y. So all we need is f prime of a. Okay. All we need is this. So f prime of x equals, remember this is x raised by half. Right, we have a half. We did this earlier. The derivative of square root of x is 1 over 2 square root of x. Then we evaluate it at the value 1 because x value is 1 or a is 1. This is 1 over 2, right? Square root of 1 is 1. 1 times 2 is 2. So that's a half. So we just write down as a y minus a, y minus 1 equals to half times x minus also 1 because the x of a and the f of a both 1. And we simplify, so we get a y equals to half of x minus half. Then move this negative 1 to the other side, become plus. So that becomes y equals to half x plus half. That's to use the formula. So that's the graph. Right, this is talking about different notations, right? Sometimes we use this notation. Okay. Okay, limits. Remember we talked about difference quotient last class, right? We have this, and we call this difference quotient. Basically, in this one, it's still slope, right? We have 2 points. We have x, f of x, and then we have x plus h, f of x plus h, right? H is a very small value. So where does this h come from? This h comes from x plus h minus x, right? We have x2 minus x1. And the top, the numerator is f of x plus y, y2 minus y1. So this is called differential quotient. So what do we do with the differential quotient? Okay, this just shows some examples of calculation, right? You see, if the function is if it's x squared, and we can go through this difference quotient to get this 2x plus h. Right? If the function is f of x equals x squared, then f of x plus h just x plus h squared, right? We can expand to get this. Then we subtract f of x, so x squared minus x squared is gone. We have 2xh plus h squared divided by h. We can factor out the common factor of h, then cancel out. So we're left with 2x plus h. So that's going through the differential quotient. So how do the derivative equal 2x except the power rule? Because we take something called limit. We take a limit of difference quotient. So this limit, that's the idea of this definition. So limit of g of x, which is read as LIM. So this means when x approaches to 8, so the graph is like this. Let's say I have a graph, something like this, right? Then a value is somewhere here. So x equals 8. So this is 8. So what does x approach to a mean? This actually means two things. X approaches a from right. X approaches a from left. So plus minus. So imagine a person walking from this direction, getting closer and closer to this point. Then that's another direction. So that is x approach A from right. Then x approach A from left. That's a -1. So this thing, x approach A, can come from two directions. Can come from the right, can come from the left. If this is a continuous function, so this L, the limit, just equals to g of A, right? Evaluation of A. Just imagine, let's say this point has x value equals to -1. Then y value is 2. Doesn't matter it comes from left or comes from right, it approaches to the value 2. Right? It's the same thing for all points on one piece of string. The only problem is, remember last time we talked about piecewise function, right? At x value equals 1, we have one piece like this, right? Then we have another piece, maybe goes something like this. Right? In this case, the limit is, we won't have limit. So for this graph, one piece of string, the limit just equals to the function value. But for this one, we see we have a problem, right? If I come from left, so when x approaches A from the left, actually from 1, in this case, just 1, from left. So limit of f of x equals to this. The open circle means it does not exist. Right? Remember, open circle means the value is omit. And from the right, maybe this is 3. Then limit of this function from the right-hand side of 1 equals to 3. And of course, those two does not agree with each other. So we say limit x approaches 1 of this function does not exist. Right? Well, sometimes maybe the graph goes to infinity. Right? Maybe you see we have a graph like this, we have a graph like this, and when it approaches 0, right? What happens when x value approaches 0? Actually, this is a graph of 1 over x. What happened? You come from the left-hand side, we see it goes to negative infinity, right? It approaches the right-hand side, it goes to positive infinity. So also limit does not exist. So that's the idea why we need the limits. We want to deal with the functions like this, piecewise function. What happens on the left-hand side of value is different from what happens on the right-hand side of a value. So this is a polynomial function. Right? 3x minus 5 is a linear function. So what's the limit of that? It's one piece of string, right? It's just a straight line. It goes on forever. There's no break. So we just evaluate. So 3 times 2 minus 5, which is 1, right? If it's a polynomial function, the limit always equals to the function value. Or let's see these ones. Right, we can think, what is the limit when x approaches 2 for this function? It's a g of x. Right. From the left-hand side, approaches 1. From the right-hand side, also approaches 1. Right, so that's why the limit exists equals 1. However, what's the function value? G of 1 does not exist, right? Because it's an open circle. Well, let's see this one. Limit from left-hand side, x approaches 2 from left-hand side, the limit, I should write a little bit higher, right? This is also g of x. On the left-hand side equals to 1. Limit on the right-hand side or coming from the right-hand side approaches to 2. So those two, of course, does not equal each other. So that's why limit when x approaches 2 does not exist. The limit exists only when they meet, like the first case, right? The limit exists because they're both heading from left-hand side, from right-hand side, heading the same spot. What about this one? This one on the left goes to positive infinity, on the right goes to positive infinity. Well, positive infinity is the concept, it's not idea. It's not a number. Okay. So we also say the limit does not exist because if it exists, it has to be a number. Remember the definition? It has to be a number. L is a number, a real number. But in this case, even from the left-hand side, from the right-hand side, heading to the same direction of infinity, but infinity is not a number. It's not a finite number. It's a concept. So that's why C is also the limit does not exist at when x approaches 2. So limit of a constant is always a constant. All right. So limit of A, if we call this identity function. Identity function. Why? Because the machine, you push in x, it gives you x. Nothing has changed. Because usually function changes the input to be a different output. But this function doesn't change anything. You give this function x, it outputs x. So it's called identity function. Nothing changed. So the identity function is just itself. What's the graph? The graph is a straight line. It cuts the first quadrant into half. First and third quadrant into half. So that's a function. That's the identity function. Every point, the x value equals to the function value. Because the limit, if it exists, it's a number. So anything we can do with a number, we can do with a limit. So the first one, let's see the property. So E for a constant multiplied by the function, we can pull out the scalar, we call scalar. Okay. Let's see if we have limit of 2x something, right? So this equal to 2 times the limit of x. Okay. And if the function is raised by r, we can pull the outside, right? If we have x raised by 3, limit, right, this is the same as the limit of x raised by 3. Okay, either direction. All right. If it's adding, we can add two limits. If it's subtracting, we can subtract two limits. We can split limits. If it's multiplication, we can split into two limits. If it's a division, we can also split into two limits. All right. The structure just carries on naturally. Let's see these examples. Right. Well, x raised by 3 polynomial function, we just evaluate 8 equals 8. Again, polynomial function, we do 5 times 2 raised by 3, 5 times 8, 40. Polynomial function of degree 3, 5 times 2 raised by 3 minus 15. That's 40 minus 15, 25. Well, polynomial like, right? So this is square root of 5 times 2 raised by 3 minus 15. That equals 40 minus 15, square root of 25, which is just 5. So similarly, we can do this one, just plug in. So we get square root of 5 times 2 raised by 3 minus 15 divided by 2 raised by 5. Then square root. So we get 40 minus 15 divided by 2 raised by 5 is 32. We just have to subtract those two numbers. So 40, we can do 39 plus 1. Then 1 minus 15 divided by 32. We get a 17. So I have 39 plus 17 divided by 32 square root. We can leave it like that. It's an irrational number. Or maybe we can approximate, use calculators. Oh, actually, it can be simplified to be 5 over 32. So limit theorem. So for all polynomial functions, the limit is equals to the function value. Limit of rational functions, p of x divided by q of x, while q cannot be 0. It also equals to, so only this condition has to satisfy, equals to the function value. Well, leave it like this, limit of polynomial, just plug in the x value, plug in x equal to into this function to calculate. Well, let's see these ones. How do we find the limit of this one? So this is rational function. So the numerator, we cannot plug in 3, right? If we plug in 3, you get 0 in the denominator, which is no good in mathematics. So what do? We can simplify it. The numerator we can factor out as x plus 3, x minus 3. Then the denominator will also have x minus 3. So these two cancel each other to be 1. So have limit, so simplify to be limit of x approaches 3, x plus 3. Now it becomes linear. Once it becomes linear, we can substitute the x value. So I have 3 plus 3, which equals 9. So I have to use a factor skill. Did I do something wrong? Oh, 3 plus 3, 6. Why did I see 9? It's not multiplication. Okay, now we can introduce the limit definition of the derivative. Right? So I have this difference of quotient. Now we're going to wrap them all together. So derivative of a function equals to limit of h approaches to 0. Right? We said that we have x, f of x at one point. We have x plus h, f of x plus h, and as a second point. But now we want to push h to be 0. Right? We can imagine if we have something like this. This is x value, right? X plus h may be on the left-hand side or may be on the right-hand side. If on the left-hand side, we just push h to be 0, right? Same thing for this. So push h to be 0. In the end, it's just this 1 point. Okay, so that is the definition of derivative as a limit. So derivative of function equals limit when h approaches 0 of f of x plus h minus f of x divided by h. So let's see this example. We want to use the limit definition to find the derivative. So f of x is 15 minus x squared. Then we need to find f of, because we want to find f prime of 5. Right? So f prime of 5 equals the limit when h approaches 0 of this. So this is f of 5 plus h minus f of 5. Then after simplification, we get negative 10 minus h. Right? Now we take the limit, we push h to be 0. So what happens? If h is 0, negative h is 0, get negative 10. So that is a derivative, right? You see the two variables has a negative relationship because it's a negative number. The slope of tangent line goes this way. This is another example. We also need to find f of x plus h. Well, we just plug in, use this function. We have the input square plus 2 times the input plus 2. Then subtract f of x. So expand this, we get x squared plus 2xh plus h squared. Then plus 2x plus 2h, then minus x squared, minus 2x, minus 2. So cancel some terms. In the end, we get this. We factor our h, simplify with the denominator. So we get 2x plus 2 plus h. Then we take a limit. We let h approach 0. When that case happens, we just get a 2x plus 2. So the derivative of this function is 2x plus 2. We can also use the power rule. Right. Power rule is the same. Take the exponent as coefficient. Subtract 1 from the exponent. So that becomes 2x. X squared derivative is 2x. Then 2x itself is linear, right? So this is linear, so the slope is a derivative. Then for constant, there's no rate of change, it's just 0. So in this case, we just get 2x plus 2. It's the same, right? So one is go through the quotient, differential quotient with limit definition. One is just using power rule. So power rule is much quicker, right? The limit, the definition is using limit, using different quotient. It's a lot of tedious calculation. But some of the questions may ask you to use, you have to use different quotient. If the question asks you to use different quotient and limit, you have to use it. Otherwise, you could use power rule. Derivative of rational function, same thing. I go through the calculation. But we also can use the power rule. I use the power rule, get much quicker. Square root of x, the same thing. Right? You could use power rule also. Okay. So when we talk about the limits goes to infinity, so have this special case, x goes to infinity, or goes to negative infinity. So what do? We use ignore rule. We ignore the lower terms. We only consider the leading term. So limit of x approaching infinity. Well, what's the leading term for numerator? This is only one term, so it's a leading term. Well, what's the leading term in the denominator? Ignore the lower term. So 1 is polynomial degree 0. So ignore it. You just have 1 over x squared. Now you can think about it, right? There's 1 over this. One apple shared by the millions, billions, the whole wide world of people. How many pieces of apple you get? This is 0. So similarly, this will only take the leading term. In the numerator, 6x is a leading term. In the denominator, 2x is a leading term. X divided by x is 1. 6 divided by 2 is 3. So the limit equals to 3. So limit at infinity. Well, let's see this one. So limit when x approaches infinity, we have 1 minus 3f of x. And this one. So how do we do that? So limit of 1 is still 1. Limit of a constant is still the constant itself. So limit of negative 3f of x, we can factor out negative 3. Then limit of x approaches to infinity, we have seen earlier is 2. Right? Because limit of f of x is 2 earlier. So do the calculation is negative 5. And when we do limit square, right, it is a limit of 1 times itself twice. And we can split as a limit of f, limit of f. Well, each limit is 2, so 2 times 2, which is 4. Okay, that covers chapter 1, 1 through 4. So section 1 up to 3 is quite light, but the section 4 is quite heavy. So make sure you understand all the examples. Then practice your homework. All right.